So thank you everybody for coming this evening slash this morning to the data analysis session on nested sampling. Right, so we already have a volunteer scribe. Thank you, uh, Michael, for offering to do that. Hopefully it won't be too onerous. I'm going to give a brief introduction to nested sampling and Bayesian analysis in the first 20 minutes or so. Andrew Caruana is going to join us, I believe, from 8:30, when he's going to give us a brief talk on where nested sampling has been used in practice in scattering or reflectometry, and take us through to a discussion where we'll have a talk about various things that are still about various discussion topics that we can generate ourselves, and I'll suggest some at the end. So, introduction to nested sampling. And forgive me, by the way, if I make any mistakes. I'm always more than welcome to take corrections to what I've introduced, what I'm going to be talking about. So if we think about data analysis from somewhat first principles, we collect a series of, we collect a set of data with uncertainties. And the purpose of our modeling process is to develop some function that relies on the independent variable x and on some set of parameters theta to develop some function that describes our data well, and to eventually refine that set of parameters so that we can derive a theoretical model that goes through all the points. So f is our function here, x independent variable, and theta the parameters. So the probability down here of observing the data, so yi is the data, the probability of us observing that data depends on the independent variable, the uncertainties, and the parameter vectors. So for the probability of observing one data point is given by this Gaussian. You have a prefactor there for some normalization. And then the argument of the exponent looks very similar to a chi-squared value. So the data minus model all squared divided by uncertainty on the data point. So that's the probability of observing a single data point. Now, the probability of you observing all of them is given by the product of those probabilities. So product of those probabilities, that has a symbol in maths with capital pi, I believe. I'm not so familiar with my Greek alphabet, but the likelihood is equal to the product of them all, big P, product. And because this is probability land, it's often better to describe, instead of a product, it's easier to describe things with a sum. So, it's better, easier to describe in log space, so that when you take the log of that probability, it turns out comes up as a sum instead. And this is then referred to as the log likelihood. And in that log likelihood, it's effectively very similar to chi-squared. And you also have this normalization term. And Michael yesterday was talking about the Poissonian log likelihood. This is a Gaussian log likelihood. So in normal least squares fitting, what we aim to do is to minimize chi-squared. or minimize the negative log likelihood, which is equivalent to maximizing the log likelihood. And what we're trying to do in a least squares analysis or in most data analyses is find the values for the parameters that best describe our model. So the red curve there is the best model, the blue line not so much. And if you're not describing your model well, you end up with systematic deviations in the residuals as a function of data point, as across the data you observe. So normally we minimize chi-squared with something like Leffenberg-Marquardt or differential evolution, minimizing chi-squared or minimizing the negative log likelihood. And what we're effectively doing in that is, as we vary the parameter value, we're trying to minimize chi-squared to get down to a minimum in that value. Sometimes, however, the chi-squared map of two parameters or of a multi-parameter system is complex, so you end up with lots of local minima, as in the graph on the right-hand side here. And sometimes, depending on the technique that you use, you can end up in local minima instead of global minima. So the aim is to get down to a global minima. And when you're in a minimum, hopefully the global minimum, the gradient of chi-squared with respect to the parameters should be 0. So the gradient of these of the chi-squared function with respect to the parameters should be 0 at a minimum, and that slope is telling you which direction to go in order to see that minimum. Leffenberg-Marquardt uses extra information, and other minimization techniques use the second order differential to tell you how fast you can approach that, how much to vary the parameters in order to get to the minimum faster. And in fact, that second order derivative is important. So the second order derivative is called the Hess of second order partial derivatives of chi-squared with respect to the parameters. So you get the leading diagonal and the off diagonal terms with the cross terms. So what's important to understand is what this represents. On the left-hand curve, I've just got left-hand graph here. I've just got x squared and 5x squared. If you look at the second order derivative of those functions, we have 2 and 10. That's fairly straightforward HSC or A-level maths. And so what we see in the red curve is that it has a tighter curvature than the black curve, whose curvature is much more gentle. And so, yeah, for F1, the second order derivative is a lot smaller than the red curve. And so just intuitively, you would expect, if you were looking, thinking of this as a chi-squared graph of chi-squared versus a parameter, if this graph is tighter, sharper, you'd expect to have greater certainty about F2 compared to F1 because the graph is tighter. So when we come to a curve fitting scenario, if the curvature is large, or if it's tight in this curve, the parameter is better defined. So it turns out that the covariance matrix is the inverse of this Hessian matrix. So if you were to invert this matrix, the leading diagonal gives you the covariance of the parameters, and the off-diagonal terms give you the covariance of the parameters. So the covariance of that leading diagonal is basically the parameter uncertainties. So why is this important? Well, in a curve fitting process, what we're actually after is the distribution of parameter values that you're parameter values can take in the modeling system. So what I've got down here on the bottom left-hand graph is a curve from a paper written by several authors a couple of years ago. Well, we're plotting the posterior distribution for a set of parameters in a curve fitting exercise. So what we're after in most modeling is these distribution of parameters, with the mean or the median giving the parameter value that we report and the standard deviation or the variance or some kind of other statistic giving you the width of that distribution. And what we see in this particular system is the covariance between all the different parameters. So if you have all these dots, if they're, I guess, distributed in a circle like this, you would expect to have no covariance between parameters. That is, as one parameter increases, another one isn't related to that. But some in the system are inevitably related, and you end up with these kinds of ellipsoids, which says that as one parameter goes up, another goes up as well. And you can have inverse covariance as well, or inverse correlation. So what, with a least squares analysis, you don't tend to get these wonderful distributions. You just get some sense of an estimate of the mean and the width, and possibly how ellipsoidal that distribution would be. But you don't see where there's other modes in the system, in the modeling system, and you don't. Yeah, it's not as illuminating. So we then fall back or go on to more advanced techniques with Bayesian analysis. And what this Bayesian analysis does is this aim in our particular application is to work out the posterior distribution of the parameters. So the posterior probability distribution is effectively represented by this graph down here. And the posterior distribution is in Bayes' equation, which is over here on the top left-hand side. The posterior distribution is this left-hand term, and it tells us the probability of seeing the parameters. Remember, the parameters are given by this theta term here, given the data and the modeling system model that you've created. So the data is represented by D here. And the posterior probability is equal to the product of these two terms on the top divided by the denominator. So these two terms on the top, the first one is the likelihood that we saw earlier, and so that's mostly comprised in our modeling system of chi-squared with the normalization term of the uncertainties as well. What I've shown here is the product. When you go to a log, this product here becomes a sum. The term on the right-hand side is called the prior probability, which is the probability of your assumed knowledge or your pre-existing knowledge of what the parameters could be. So for many systems, that probability distribution might just be a uniform distribution if you just know an upper and a lower bound. Alternatively, you might have more information about the system that leads you to believe that you might have data from another measurement that says, hey, well, our density is actually a Gaussian distribution, so we might expect it to have a mean and a width. So yeah, instead of an uninformative uniform distribution, we may have more information in there. So yeah, this prior term might be like any kind of distribution, probability distribution. The term in the denominator is called the evidence, and that's the probability of seeing the data given the model. So that's basically the entire probability of the modeling system. And that's the normalizing term for this product or sum in log space of this right-hand side of the equation. And I believe Bayesian analysis was first applied to reflectometry or scattering by somebody called Devinder Sivia in the 80s and 90s, and it's enjoyed a resurgence in reflection in the noughties when as computers got more powerful. So there are various probabilistic modeling packages available in Python, particularly. It's very strong for this kind of thing. And the ones that are worth mentioning, the Python packages worth mentioning for doing this kind of posterior sampling are bumps, PyMC, and MC. And they typically use something called Markov chain Monte Carlo, which is a stochastic process, typically consisting of a chain that then evolves over a period of time to explore this probability distribution. And they're great for obtaining the posterior, but not so great for understanding and finding out the denominator in Bayes' equation, which is the evidence term. So the evidence term in the denominator is this integral, and if it's basically the integral of the likelihood and the prior over all the different sets of values that the parameters can take on. So it's kind of intuitive, right? You're basically integrating. You're trying to normalize the top, so you have to integrate over all of that space. And something that made sense to me, and well, it's perhaps obvious to you, perhaps you already know it, but what you're trying to do is integrate the likelihood over the prior volume. So all the different values that the prior can take on, you're trying to integrate the corresponding likelihood over those parameter values. And the important thing for us is that the knowledge of this evidence allows you to compare two different models. And so why is model comparison important? Well, it allows you to go, say, in a system like this where you might have several competing models. Here in the graph on the bottom left-hand side, we have some simulated data. And we can say, well, hey, we want to fit this with a Gaussian, but should you be using one Gaussian or two Gaussians or three Gaussians and so on? And you might say, well, that's perhaps relatively easy to do. Well, we know that there's at least one peak. It's definitely not no peaks. One peak would be a lot more probable. Because we see the shoulder on the right-hand side, we might say that two is even better, but is there a third one here? And this model comparison allows you to quantify this. For scattering, this might be instead of like 1, 2, 3 Gaussians in a quasi-elastic neutron scattering system. It might be, well, are we going to be using one Lorentzian, two Lorentzian, three Lorentzians to fit this peak? In reflection terms, this might be, well, hey, we've described our model with a series of slabs. Is it going to be like a 1, a 2, or a 3 slab model? And typically, the heuristic that we've used in the past is use the minimum number of slabs that gets you the best fit. But this allows you to quantify what you should be using, which is quite useful. And so uh, typically what we're what we're doing in this, so here we've got like a ratio of the evidence terms. So this might be the evidence term for model B divided by the evidence term for model A. And remember, P of D type B or IB, that's the probability of seeing the data given the model. What we're doing is comparing the ratio of those evidence terms there. We've got a couple of two extra factors there, which are your that's the prior for you thinking that you should have had B in the first place compared to A. But what we're effectively doing is looking at the ratio of the evidence terms on the left in this first quotient. And when you figure out that quotient, um, you can use that quotient to figure out, well, hey, the evidence for the more complex model, if the different the the quotient or the log quotient is say 1 to 2 in the log quotient, that might indicate that model B is supported. Uh, you have strong support for model B compared to model A. Greater than 2 would be decisive, but like if the difference in that quotient or uh, difference is not big, then yeah, there's not really much evidence for this. And what I'd like to do here is just through Andrew McCluskey's, he's got some slides or an open source book on this, and I'd really like to suggest you going to read this set of information that he's developed for modeling purposes is quite illuminating and a good teaching source. So how do we go about estimating this evidence? Uh, we use a term, we can use something called nested sampling. And this nested sampling approach was first suggested by somebody called Skilling. And there are a variety of Python packages available to do this. One of them, some of them are listed on the right-hand side here: Dynasty, Multinest, Ultranest. There are others. And they typically take what they require is an some typically some transform that tells them what the prior volume is. So that is what areas of prior that for the parameters that they can explore, and the likelihood corresponding um, to the log likelihood for a set of parameters, which, where as they go exploring this space, that they can use uh, to adjust the sampling process. And so all of these, all of this nested sampling, indeed the Markov chain Monte Carlo, is a fancy way of doing integrals in multi-dimensional space. And remember, what we're doing with to estimate the evidence here is that we're trying to integrate the likelihood over the prior volume. So that is basically what's the volume of what's the integral, I guess the volume integral of the likelihood over the prior volume, which is described or which is illustrated in this contour plot over here. And what we're showing is the different likelihoods as a function of prior mass. So you can imagine down here this L1 position will encompass more of the prior mass, but it has a lower likelihood. And what this nested sampling does is that it gradually goes through stepping in through this slowly concentrating in on a prior mass to estimate the volume um, of the likelihood over that prior mass to give us the evidence. So this algorithm, this is a bird's eye view of the algorithm. I'll step through this slowly. Hopefully you can follow me as I go along and it will all make sense. So you start off with a whole series of points, parameter values theta, that are sampled from the prior. So 100 points, 500 points. And then the first thing that is then an iterative process to estimate the likelihood. And the first step that you do is you take all the points and you work out the current likelihoods, uh, effectively chi-squared in inverted commas, of all those parameters, theta, sorry, all the different parameter vectors, and work out the likelihood for all those parameter vectors. You find that the one with the lowest likelihood, so that would be the highest chi-squared, lowest log likelihood, or the lowest likelihood, that would be depicted with a capital L here. That's the lowest likelihood. Or L is likelihood, but you're trying to find the parameter vector with the lowest likelihood. You then work out the I think X is the prior mass. And as you go through this loop, the prime mass starts shrinking, which is why there's an exponential term in there, which is related to the number of times you've gone through this loop. You then have derive a weight, which is related to how that prior mass has shrunk in since the last iteration, and then you update the evidence term with the the likelihood, which is the least likelihood, and the weight. You update that evidence term, and you go through this iterative process, updating the evidence term. And once you've gone through, that iterative process, you end up with the likelihood. So that's a bit of a top level view of what I've attempted to do, is reduce it to the to simplify it. But effectively, all these programs take care of this for you, and you just need to give them your priors and your likelihood, and it takes care of that sampling process for you. So where I particularly use this in reflection is to look at polymer brushes. So a polymer brush is a polymer chain that's end grafted to a surface. And typically what we do is we have what we do in our modeling is to describe this structure with what's called a polymer volume fraction profile. And we model this volume fraction profile with over here on the left-hand side, we typically use a spline system. So this interpolating spline allows us to have a wide variety of flexibility in our volume fraction profile. So you can take on a wide variety of different volume fraction profiles to give you, which can then be converted to a scattering length density profile. But one of the things that we wanted to do in this, is say, well, how many knots should we be using in our analysis? Is 1 knot sufficient? Do you need 2 knots, 3 knots, 4 knots? And what the nested sampling allowed us to do is figure out, how many knots we should be using. Because if you use a smaller number of knots, that's much more, it's easier computationally. So we can work out the evidence for using 2 knots. That log evidence is 168. Then if you use 3 knots, you shoot it rapidly because there's a cut in the axis here up to like 257 odd. But if you start using more than 3, 4, 5, 6, you stop increasing in probability, and in fact you start to decrease. So here we probably want to be using at least 3. You can probably use 4, but there's no justification to using 5 and above. So we published that work a few years ago, which is a paper looking at the robustness of reflection for looking at for using reflection for looking at polymer brushes. And also, so like that nested sampling would also allow you to figure out, well, these two models here describing this reflectivity curve, there's not a huge number of fringes in there. There are some subtle fringes like that there and here and there, but not a huge amount of detail otherwise. And what nested sampling allows you to do is figure out the relative probabilities of the blue model and the orange model, which otherwise would give you quite similar reflectivity curves.